All right, so please feel free to interject. I have less than 25 minutes worth of slides. And the goal of this talk is largely just to give you a sense of some of the tools and techniques that exist both in the theoretical and practical domain that go into dealing with the fact that data distributions change all the time. So you all have probably seen a fairly canonical learning paradigm picture, something like this, right? Where there exists some distribution, some data set S is drawn i.i.d. According to that distribution, which is given to some machine learning algorithm, which then produces a model, right? The model, then the goal of the model, or what the model will actually be used for, is making future predictions of some y's for some new x's, which are drawn from the same distribution, the same marginal distribution over my set of features x, as the original training data was drawn from. Right? So this is a fairly standard picture, right? And you know, in general, the goal is to learn a model with good performance, being somewhat abstract about what I mean about that, on this future data set S prime that we don't see when we design the machine learning algorithm and therefore pick the model. And in general, right, how do we do this, right? We in general optimize on S because we don't know S prime, while trying to avoid just memorizing S and trying to learn something about the distribution D from our sample S, right? And the way we generally try to avoid overfitting, well, there are a bunch of different things, right? But you can think about various types of constrained optimization, right? You can think about regularizing whatever you're trying to do, which is like approximately trying to remember how to map X to Y from S, right? You can think about limiting your model complexity or penalizing higher complexity models in a variety of different ways, right? And this is sort of the first, ML 101 standard model for how, when we know sort of how to prove things and how to say, this is how we generally will produce a model for which we can give some theoretical guarantee about its performance on data drawn from the same distribution. So unfortunately, right, in a lot of cases, if you use, while this is a beautiful and rich theory there's a beautiful and rich theory of when and how to do that earlier initial picture of machine learning, I will be maybe somewhat contrarian and say that it's a model that is largely overly simplistic compared to most of the problems we will see in practice, right? Training and test data are almost never distributed according to the same distribution. Right? And there are many reasons for that. One of which is somewhat easy to say, is that your training data was gathered before you trained your model, and your model is presumably being run on some data that was drawn from perhaps some later time, right? And the passage of time leads to drift in distributions, right? In terms of the features you see, in terms of the labels that you see and the relationship between those features and labels. And we often have multiple data sources, right? It's often the case in many practical applications, a data set isn't sort of drawn from some like magical fountain, which is a single distribution, right? People have come up with some procedure for like scraping images off of Flickr plus, maybe some other website, and the combination of those are then post-processed in some way, right? So if that's the case, it's not exactly right to say that even the training data is i.i.d. Some of our data might be unlabeled, might have auxiliary features, and likely follow different distributions, right? So while this initial picture of sort of training a model to work well on data which is drawn identically to the same distribution as that which we trained upon, it really has a limitation in the sense that in general, you have no guarantees. You have no guarantees for free for future distributions which are different. And I see a hand, Ali. or is that a mistaken hand? Okay. All right, good. Okay. So one example, right? If you're thinking about like, what do you mean that like merely the passage of time could lead to drifting distributions? Well, think about the following, right? Suppose you collected a bunch of data that was like shopping data on Cyber Monday, for example, right? In the United States, the Monday after Thanksgiving is like a very busy online shopping day, right? And if that was the data you trained upon, right, and then you tried to use that model for people who are to do some prediction task for people who are shopping on Tuesday or maybe the following Monday, right, you would likely see quite different behavior on Monday than you would on Tuesday. Right? And that doesn't mean there's nothing in common between these problems, but it does mean that, you know, even just one day apart, right, the behavior you might see if you trained on Monday and tested on Tuesday might be quite different. And you might ask what the goal would be in such a paradigm, right? Previously, like when both S and S prime were drawn from the same distribution, there was a fairly well-defined goal, right? And you know, there are several approaches that you can think about to sort of try to guarantee you have good performance on S prime here, right, where S prime is no longer drawn according to the same distribution. If you're not a machine learning researcher and you don't know, or you don't know about sort of the latest and greatest techniques for handling some of these things, your first attempt might be to just use everything from that first model and just see how well it works, right? And if it still kind of works and it doesn't require a bunch of extra engineering, maybe that was like the best strategy to begin with. Generally, I would push against it being the best, but it is in fact like what maybe often happens in practice, right? But there are better ways generally to handle the fact that your data distribution might change over time. There are, you know, a variety of things, and I'll give you just a brief introduction to a few of them. So one is to sort of parametrically model the shift, right? And in the case of shopping, but also in the case of many other things, people make explicit assumptions about what they expect the data change to look like, the distributional change to look like. And if you do that, right, then maybe you just have some small number of parameters to try to learn before you quickly can adapt your model to working well on Tuesday from Monday's training. That's one approach for handling these sorts of things. Another is something I'll talk about a bit more in a moment, which is rather than thinking about training one time and producing a model and then, you know, using that forever and ever going forward, right? Many of the people you've heard from throughout the day are people who think about learning online, right? And online learning just means that rather than picking one model from a batch of data and then leaving it forever and using it forever, that you should instead be constantly updating the types of predictions you're making based on the data you've seen recently, right? So that is one approach for handling some of this stuff. And there's another family of approaches for handling shifting data distributions, which, you know, I sort of like to, broadly speaking, refer to as hedging against likely D2, right? Against likely distributions you might see in the future. And I think that this is somewhat philosophically different than assuming absolutely nothing about like the future data you might see. But I'll tell you a little bit more about each of those things. Okay. Sorry. Okay, so right, in reality, the picture is even maybe more complicated than the thing I just showed you, right? Maybe we have many, many different distributions that are generating data, and we don't even know what we're going to be tested upon. So just, you know, to further push this point home a little bit more, I think it might be useful to think about the following application. Imagine that we have a bunch of different hospitals that are geographically distributed and have really, really different demographic populations. Right? They might be gathering some kind of data, each individually about their local population's health. And it would be really nice to be able to learn from one of these hospitals that maybe has a much larger data set, say in Manhattan, and apply what we've learned there to something like Anchorage, right? But those distributions are fundamentally different, right? The set of people who are patients in those hospitals is very different. And everything about the movement and day-to-day life of people in those communities is different. So there is perhaps some fundamental relationship, right? If you're studying a particular disease of interest, right, there are probably some commonalities that you should be able to find. But it's not at all clear how to take something you've learned from a patient population in Manhattan and apply that to something meaningful for people in Anchorage. Okay. So now I'm going to give you just, like 3-minute summaries of 3 of the standard sorts of approaches for dealing with some of these issues, right? And this is mostly just to give you a sense that there are a lot of different techniques and tools for handling some of these things, and they all have their strengths and weaknesses, right? So let me first briefly tell you a bit about online learning, right? So online learning generally works in the following model, right? We assume we have some algorithm, right, and an adversary. And the adversary produces a sequence of examples, which are then given to the algorithm one at a time. And the algorithm has to make a prediction about a label for any particular example. And this happens repetitively, right? Maybe up to T rounds, for example, right? So the algorithm, all the algorithm knows is it's seen some sequence of X's at some period of time, and it's made some set of predictions Y, and maybe actually gets to see the loss or the error of those predictions, right? But it doesn't know, and in fact, necessarily cannot know anything about the future X's it might see. And has to sort of guess and sort of hedge against all possible relationships between X's and Y's that aren't completely ruled out by what has been seen so far. Right? So here, right, the goal of a machine learning algorithms researcher is to think about how to design this algorithm in this box to perform nearly as well on the sequence X1 through XT, nearly as well as if the algorithm had seen all of X1 through XT and all of the losses for Y1 through YT and any other possible Y1 through YT that they could have chosen in hindsight, right? So this is it's kind of a weird philosophical thing, but imagine you had all of the information about the XY pairs. There would have been some, if we're thinking about machine learning, some fixed model in the class that A was thinking about that would have had the lowest error. And in general, the goal in online learning is to try to compete with sort of the best thing had you known everything about this online instance at once. And this is something that is very much an active area of research. But there are many ways to design algorithms which work well in an online setting. Yes, I see the question. Okay, cool. Good. So I'm seeing a couple of questions, both of which are great. So the first question is, can we think of this like ongoing ERM? And the short answer is maybe, right? So there are variants of online learning where you make more or fewer assumptions about exactly what the adversary is doing, right? But yeah, you can sort of think, one way you could think about trying to solve this problem is just running ERM over and over and over again on the set of examples that you've had and you've gotten the feedback for the decisions you've made, right? Now, that in general is that's usually not a good strategy, right? Strategies that sort of assume that the information they've had in the past will be the best predictor of the future actually generally don't work as well for this kind of setting. But there's no reason to believe that would definitely be the first thing that you would try, and then sort of convince yourself that an adversary can really screw up ERM almost every time. Okay, and then the next question, would this hindsight fixed decision need to be a single constant function, or could it be defined as a function? Yes, so that's also a great question. Let's imagine for the moment, although this could be many different things, let's imagine the algorithm is picking amongst linear functions, right? Let's assume that it's sort of like each day after, on day 7, it's seeing x1 through x6 and making predictions y1 through y6, and then seeing actually the true labels y1 star through y6 star, right? And let's assume that for day 7, right, they're going to pick a linear function and they're going to apply that to x7 that they haven't seen yet before, okay? Let's imagine, right, in that world, you can think about the algorithms like hindsight strategy being a fixed linear function, right? One that doesn't change every day, right? And in general, right, there are a bunch of different ways we can like sort of say what we're comparing, what our benchmark is. So, I'm trying to specify enough so that it makes some sense, but not so much that I'm actually talking a lot about the details of my mind. But in general, right, there are algorithms that work well in this setting, in the sense that they sort of approach doing nearly as well as the best fixed strategy in hindsight, as the number of days t grows very large. They generally do look, they do learn something from the past, right? Generally, they're not quite as tailored as ERM, right? They generally have some kind of regularization or hedging component to them. So, you could call ERM something like follow the leader, right? Basically, you look at the last 10 days, what was the model that would have worked best on the last 10 days, play that on day 11, right? There are a bunch of reasons why that doesn't actually work well, but if you do some regularization, suddenly that works much better. What names could you look up to learn more about these algorithms? So follow the regularized leader, weighted majority, randomized weighted majority. If you look up online learning algorithms, there's a huge literature. There's also a really nice chapter. There are a few nice chapters in like existing textbooks, which maybe Ellen can throw some stuff in, or I can throw some stuff somewhere after the talk. Cool. Okay, yeah, and the whole point of this is largely to give you a sense that these things exist, not to like tell you too much about them. Okay. All right. So what are some of the pros and cons of using an online framework to deal with shifting data distributions? Well, the pro is that algorithms that were designed to perform nearly as well as the sequence of the best fixed decision in hindsight generally do that, right? In the sense that like they have that theoretical guarantee, and so they satisfy that guarantee. On the other hand, right, this approach and this model of the sequence of data that are presented to the algorithm really being adversarial is often more pessimistic than what actually occurs in practice, right? You might say like ERM is too optimistic and this online paradigm is somewhat too pessimistic, right? And your algorithm is having to hedge against all sorts of different things that the adversary might do, many of which are probably not plausible, but even trying to hedge against them, right, can really impact an algorithm and a model's performance in many practical applications. Okay. So now I'm going to give you the world's shortest description of transfer learning, right? And again, this is an imperfect and partial description. But let's think back about this example I gave a couple of slides ago, where we have some labeled data, which is collected on Monday. And I've perhaps trained a model, or at least like I've gathered a bunch of data. And I have another distribution, which is Tuesday's data, right? And maybe I have even some unlabeled data that is drawn from Tuesday's distribution, but I don't have labels for it, right? I have labeled data from Monday and unlabeled data from Tuesday. And the question is, with the labeled data from Monday and the unlabeled data from Tuesday, can I somehow like do a much better job making predictions for Tuesday than if I had either of those by themselves, right? Okay, so that's where transfer learning comes in, right? Transfer learning basically asks, is it possible to take a bunch of labeled training data from one distribution, some unlabeled training data from another distribution, and build a model that actually works pretty well on unlabeled data from that second distribution. So the goal here is, again, to learn a model with good performance on this, like, this distribution, this data drawn from this unlabeled data distribution, right? And, in general, this should not be possible, right? Without more assumptions, right? Like, I have a bunch of labeled data from one distribution, and I have another distribution for which I have unlabeled data. There's no reason to believe that the relationship between my labels and my features has anything to do with one another on these two different distributions, right? However, if I believe for some reason that there is going to be this relationship, right, that there is going to be some similarity between the relationships between X and Y on these two different distributions, there are approaches that, if basically I believe that, like, the relationship between X and Y stays relatively fixed, right, then there are some things you can do, right? And some names of them were just there. So if you're interested in this sort of thing, there are various approaches, right? Reweighting schemes is a nice thing. There are lots of other things that live in this space. This is like just a partial list. And in terms of pros and cons for these sorts of approaches, right? You don't need labeled data from the target distribution, which is what we call this unlabeled data distribution in general for culture, right? The dark green labeled data distribution is called source, and the unlabeled lighter green distribution is called the target in transfer learning speak. In terms of cons, right, this generally only works well when your distribution of Y conditioned on X is fixed. But maybe your distribution over your features is changing. That's not universally true, but that's like, sort of the brainchild of when this works best. And it works best, again, when there's positive probability on all of your X's for both of your distributions. Okay. So now I'm going to say, again, the world's shortest description of one other approach to thinking about dealing with shifting distributions, and that's what's known as distributionally robust optimization. And distributionally robust optimization says, okay, I have some data distribution and presumably some like finite sample from it, right? And my goal is to pick a model which works well for any distribution which is sufficiently close to my training distribution, right? So here I've drawn that I have like, I have my original distribution in dark green, and I have this sort of circle around it, which represents like the distributions which are not too far away from that original distribution. And the goal of distributionally robust optimization is just to build a model that works as well as possible over that entire region of possible distributions. And good question about the distance metric. Pick your favorite distance metric over distributions. Yeah. So the goal here is to hedge against distributions which are close to your training distribution. And there are lots of optimization tools to actually, design a model that sort of minimizes the maximum loss that you might see for any distribution which is close. And this does give a lot of robustness against all sorts of types of distribution shift, right? Assuming your distribution doesn't change wildly, right? It allows for changes in X, changes in Y conditioned on X. Lots and lots of types of distribution shifts are handled under this model. But again, there is some like pessimism. Generally, it's hard to know how large a region of uncertainty needs to be, right? And you get this weird phenomenon where, like, if you slightly overestimate, right, especially in high dimensions, right, slightly increasing the radius of this ball, suddenly, like, you have like way more distributions that you're having to hedge against. Okay, so I'm all wrapped up. Right? But, if you assume nothing about your future data, right, like that it really may have nothing to do or an arbitrary amount to do with the data you've seen so far, online learning is usually the first thing you should think about, right? If you believe that there's a huge amount of similarity, right, between train and test, and maybe just something about like, the distribution over your features is changing, but like fundamentally the task of predicting y from x is staying relatively constant. That's a world in which transfer generally works best, right? And somewhere in between, right, I would claim distributionally, in a philosophical sense, distributionally robust optimization lives, right? It believes that there is some relationship between your training data and test data, which online learning does not assume, but it doesn't assume much else besides like training and test distributions not being too far apart. Well, thank you all very much, and I'm happy to stick around for some questions.
Yeah, thank you so much, Jamie. I think there's another question we can get to before we move on to Clement's talk. Would another meaningful general approach be to consider the shifts to correspond to some kind of truncation on a ground truth distribution?
Sorry, I live next to a gas station and someone's playing very loud music outside with like the craziest bass you've ever heard. Okay, so yeah, so certainly that can be a meaningful approach in some cases, right? I would say that kind of approach would like lie within this sort of parametric modeling to some extent, right? You know, depending upon how much you know about your learning problem, right? There are all sorts of fancier things you can do with the information you have, and you definitely should exploit all of the like domain specific knowledge you have for your learning problem, because you know machine learning is, like it or not magic, and it works way better if you try to encode the things you know about the prediction problem you have into the model and algorithm that you build.